Hello, my name is Kamal Dous, and on behalf of my co-authors, I'm excited to present Emergent Social Learning via Multi-Agent Reinforcement Learning. This work is motivated by the importance of social learning to human cognition. Individual humans can learn to accomplish a very wide variety of tasks. For example, we can read and write books, participate in geopolitics, and run space programs. It would be very unlikely that solitary humans could develop the skills necessary to perform these tasks in isolation. Rather, we learn to accomplish these tasks with the help of experts, through, for instance, verbal or written instruction, formal schooling, or pure mimicry. Furthermore, we're able to learn from each other without direct access to the experiences or memories of other humans. With humans, all teaching and learning is mediated by our shared physical environment. Social learning could help AI agents learn faster, explore safely, and adapt more quickly to new environments by taking cues from human experts. For example, person-following robots could avoid unsafe areas by taking cues from humans who already know how to avoid areas where they might get hit by cars. And domestic tasks like unloading dishwashers pose a significant robotics challenge due to the variety of specific dishwasher configurations. A household robot with a human-like capacity for social learning could learn how to unload a certain dishwasher by observing a human complete that particular task variant. In these examples, the human experts don't naturally generate trajectories or policies that the robots could use for imitation learning. With that in mind, this work focuses on independent multi-agent reinforcement learning, where multiple independent agents interact in a shared environment. They can see each other, but both training and execution are decentralized. We also focus on scenarios without strategic interactions, where agents are rewarded separately, and where agent rewards don't depend explicitly on the rewards garnered by other agents. We introduce a novel, hard exploration, sparse reward environment called Goal Cycle. In Goal Cycle, agents are incentivized to gain valuable information by observing experts, rather than by risking penalties and exploring themselves. But even with this environment designed to encourage social learning, we find that agents trained with vanilla model-free reinforcement learning struggle to learn social policies. We mitigate this issue with an auxiliary world modeling objective. This auxiliary loss allows agents to learn useful representations, even when they don't have enough skill to collect rewards. The combination of the goal cycle environment and the auxiliary prediction loss allows agents to learn generalized social learning policies. In the goal cycle environment, agents navigate between three visibly indistinguishable goal tiles. Agent observations are image renderings of the tiles in their vicinity, shown on the right side in this video. They're rewarded for traversing the tiles in the correct order and penalized for making mistakes. In each episode, agents must discover the correct ordering through trial and error, sometimes incurring penalties. Agent colors are determined by their rewards. They start off red and become slightly more blue when they receive a reward, only to reset to red when they're penalized. This prestige coloring scheme is the only feedback agents get about their own performance during an episode. It also signals skill to other agents in the environment. We find that agents trained with vanilla PPO perform poorly, even when trained in the presence of experts. This is because model-free RL algorithms struggle to learn when the reward signal is too sparse to induce informative gradients. In our paper, we show that this is the case for both policy gradient and Q-learning algorithms. However, agents trained in the presence of experts with the auxiliary predictive loss, shown in green, learned to perform very well. They performed as well as agents trained by imitation learning, but in addition, since they were able to avoid exploration penalties, they often exceeded the performance of the experts in their environments. When we train novices in high-penalty environments in the presence of experts, they learn to infer the correct traversal order by watching the experts, rather than through trial and error. In this video, the social learner, whose view is highlighted in red and shown at the top of the column on the right, waits for another agent to identify the correct order before following them for the rest of the episode. So far, we've found that agents trained in the presence of experts in the goal cycle environments were able to use social learning to perform well. But this is a bit hollow, since fundamentally what we've done is solve an environment of our own construction. What good is this? Well, we find that social learners trained in goal cycle are able to perform well at other grid world navigation tasks. Here we compare the zero-shot transfer performance of the social learners in a guided maze navigation task to other agents that were also trained in goal cycle. The social learners, shown in purple, outperform solo learners as well as the three goal experts and imitation learning experts. So the social policies learned in the goal cycle environment help agents perform well in navigation tasks other than goal cycle. Our paper examines the versatility of social reinforcement learning, finding that social policies emerge when the experts are imperfect, and that a mixture of social and solo training can yield agents that perform well in both social and solitary task variants.